Okay. Now, next, still, oh, wait a second. Before I start, I just want to make sure. So this session is still like 15 minutes. So it ends up like, yeah, so anyway, let's start. So in this session, I will still keep going to apply our framework for other kind of offline imitation learning. So other kind of offline reinforcement learning task, like here, we just apply this framework for offline imitation learning. So as I mentioned, usually imitation learning is that you are given a lot of expert behavior policy, and you want to make sure eventually you find a policy such that the policy performs similar to the expert behavior policy. So simple, like still this constraint. Basically, you want to find a stationary distribution of the current policy, but you change the objective function into, say, like minimize the d pi with respect to the dd. dd you can think now is expert behavior policy. Roughly speaking, this is ensure that your policy will behave similar in terms of stationary distribution to the expert. So quite simple, right? Still with everything similar, Lagrangian formulation, importance sampling, and eventually it came out like this formulation. Quite straightforward, right? So yeah, nothing too much after you understand what we have experienced before, this optimization and policy evaluation. So quite simple. Yeah, okay, let's see next. Okay, here I don't want to show the empirical study, but if you're interested, please refer to this paper. Okay, next is a little bit difficult one, which is offline confidence interval estimation. As I mentioned, previous estimator, for example, the offline policy evaluation estimator, only give you a point estimator, which means every time you have a single scalar to approximate expectation. But sometimes we know the confidence is important. For example, a lot of people in offline policy optimization, they don't maximize the point estimator. They maximize the lower bound estimation of the point estimator of the policy value. Due to some justification reasons. For example, robustness and so on and so forth. But anyway, I just give you an example that where the confidence interval estimation is useful. So then it raises the question, how can we estimate such kind of confidence interval with offline data? One straightforward idea actually from statistics is very simple. I give you a data set, and you construct data set by resampling from the original data set to construct a lot of sub data set, say like DI. And for each of them, you run the DICE estimator on this data set to obtain one point estimator. So remember, you run that m times, so you will have m different estimators. And now you just compute the variance based on this estimator, which and you can plus them and minus them to perform as both upper and lower bound for the confidence interval estimation. This is called bootstrap. But major problem of this one is it's sometimes too expensive. You know, every time you need to solve a min-max problem, and it's m different set. So you need to run m times, so it's not very good. So the nature question is, could we have a better way to do the policy offline policy confidence interval estimation, which is more computational preferable in a more efficient way in terms of competition? The answer definitely is yes. That's what I will represent here. But before we go there, let's first check variational representation of the lower bound. I first explain some notation here. So this C is some scalar, and this Sn square is the variance of your estimator. This Z is some random number, and it is taking expectation with respect to sample. So this part is the empirical sample estimator, and the S are just the variance of this estimator. Okay, this is just saying with you solve this optimization, and this can be represented as lower bound because you see you move this side here, it's bigger or equal to expectation minus this square root of variance. And also you move this to here, it's upper bounded by expectation, your empirical variable, your empirical estimator minus some quantity which is related to your square root of variance. Roughly speaking, when you solve this one, it gives you quite a good estimation for expectation plus its square root of variance. So actually, this quantity is used a lot in distribution robust optimization. Okay, and also it's highly connected to an estimator called empirical likelihood. But I'm not going to that detail. But remember, this is just a special. This optimization, it's just a special representation of expectation. Empirical expectation minus square root of its variance minus standard deviation. I provided some proof sketch here. So let's denote U as 1 over n minus W. So I can rewrite this object function in this formulation. So instead of optimization W, which belongs to a simplex, I focus on its 1 minus n minus W. I do a variable change of variable. And particularly, this df, f divergence, is utilized the chi-square, which f belongs to, f is x minus 1 square. So with this plugs into this optimization, I eventually get this optimization. And then we can see we achieve the maximum over this part by Cauchy-Schwarz inequality, which gives you this optimization, this upper bound. And it's achieved this upper bound if and only if we know it's unified distributed like this formulation, like this. Okay, and then we need to make sure it belongs to the feasible set. So yeah, this part is ensure we have U belongs to 1 over n. So this together gives us the right-hand side of the upper bound. I'll just plug this in back into here, and eventually, yeah, expectation minus what you have here with this quantity is more than equal to square root of the variance, basically standard deviation. I think this lemma is used quite a lot in the distributed robust optimization. Okay, and for the right-hand side, it's also not difficult to prove because when we assume they belongs to they is bounded, and previous assumption, previous conclusion is come from the condition that this one always satisfied, which means we always have square square of s bigger and equal to this quantity. But if it's not, we immediately have this count. If it's not, it's saying, okay, if it's not, this part is 0. So definitely you minimize W in this simplex, which means you pick the smallest one among this Z, and it's definitely smaller than your expectation, empirical expectation. So this gives you the left-hand side inequality. And now this basically gives you the variational representation of the lower bound. And similarly, we can also have a similar formulation for the variational representation of upper bound. Instead of maximized weights in the simplex, you just do maximization instead of minimization here, which gives you the expectation, which approximate the empirical expectation plus the standard deviation. And actually, that is what we want, right? Which means if you have some estimator and you don't do this empirical estimation, but you find some weights in the simplex while it's not far away from the uniform distribution on this data set. And then it will give you a variational, it will give approximation for both lower bound and upper bound by either do minimization over this section or maximization over this section. So based on that understanding, we have this CoinDICE for offline confidence interval estimation. How we deal with that? Remember, we have L, which is basically considered as Z in the representation here, this Z. And then you introduce this minimization over the reweighting part. Instead of use uniform sample, you do minimization in this simplex. It will give you lower bound. Vice versa. Oops. Here's a typo. It's not minimization. This should be upper bound, and this should be maximization. What I have done. Okay. This basically gives you both lower bound and upper bound by switching in this reweighting on the observed data set. Okay, until now, are we clear about the CoinDICE formulation? Yeah, any questions about this one? Okay, good. And then we basically, actually this proof is quite straightforward if you understand that, okay, what we observe, what we optimization actually is approximation of this expectation plus or minus this square root of variance. And then you utilize some probability inequality, for example, this one from the Marot and Portil 2009, and it directly gives you this confidence with high probability. And you don't need to worry too much about what else. So I think this is quite straightforward. If you have that kind of you understand that optimization actually is a variational representation of lower bound and upper bound. It's not difficult. It's quite straightforward. Okay. Until now, I think I finished the how we can use this kind of dice family for offline confidence interval estimation, and also provide a theoretical guarantee. And next, I will definitely to show the empirical performance of that algorithm. Before I start here, any questions about this part, method, and also the theoretical guarantee? Okay, silence. It seems like we don't have questions here. Oh, everyone is totally lost. I don't know which one. But anyway, I assume we are on a good track. And now let's see the performance. Okay, so we compare to some existing method, which is bootstrapping. And there's also existing method you directly Bernstein with IPS. IPS, remember the inverse propensity score method, which is basically doing important sampling with some Bernstein correction for the upper and lower bound, and also student T, which is a asymptotic method, still based on IPS. Let me explain a little bit here. The figure is not clear, but let me explain it. So we tested on two environments. One is called frozen lake, also from the OpenAI G for reinforcement learning, and the other one is taxi, which is a simulator quite applied, which is quite popular. The upper row actually is trying to evaluate the quality of the confidence interval, which this black dot line actually is expected how many times the estimator should how many times your confidence interval should cover the ground truth. The closer your curve is to this dot line, the better it is. You see the confidence and the x-axis actually is the 1 minus alpha percentile. So the larger it is, you will feel more confidence about it. But correspondingly, this bottom line is the width of the confidence interval. So the larger it is, the wider it is. So that's understandable. And you see, our method is much closer than competitor to this black dot line, which means the confidence interval get from CoinDICE is better in terms of the coverage rate. And later, the bottom line is actually the log width of the estimator, which means the smaller, the better it is. And compared to the rest of the competitor, our method achieves the smallest confidence interval, which means our estimator is both tighter and accurate. Yeah, that's how to interpret this empirical study. Okay, so if we don't have any questions about this off-policy imitation learning and off-policy confidence interval estimation, we will go to a summarization of this offline reinforcement learning design method according to this primordial framework. Actually, we already see many problems can be recast as an optimization and then utilize the regularized form and the important sampling ratio formulation. We can solve it only according to the offline data. So here this part shows algorithm, which means we have several papers along policy evaluation, policy optimization, policy imitation learning, and offline confidence interval estimation. And this side is several papers for theoretical guarantee for these algorithms. Yeah, for particular paper, actually it's listed in the reference in the end of the slides. Until now, I think we finished the section 2, and here comes the summarization of the section 3. As we already observed, the optimization, especially the linear programming reformulation, actually provide a unified framework for offline reinforcement learning. And meanwhile, it helps us to establish better statistic and optimization property. And also, you can see based on this framework, we can design a lot of principal data efficient reinforcement learning algorithm. Meanwhile, it's very easy to compatible with the neural network on other kind of nonlinear parametrization generalization into the algorithm. But still, there are some open questions. If you notice what I introduced, I never mentioned how I solve the min-max problem when I list it. It's just because if it's convex concave, we know everything. And if it's neural network parameterized, well, I'm not saying we don't know anything, but we know very little. So that means we need a relatively look into how we can solve such kind of stochastic approximation problem in the form of a min-max optimization. This is quite difficult. I know Niao, Professor Niao is an expert in this area. So yeah, but it's still a lot of problem is still open. Yeah, the second part is still related to this one, especially when we use neural network into the min-max formulation. We know statistical property for that, for the optimal solution, but we don't know how to achieve that. It's a little bit awkward. Okay, finally is something I'm personally not very satisfied, which is the data coverage assumption. As we already noticed, in all the theory approved and all the theoretical guarantee, we always need such kind of assumption because we are restricted in the, we are utilize the tools from the statistical machine learning theory, which can only give you the generalization on the same support. Although there could be some distribution shift, but the distribution shift is limited to the scenario where the support is the same. But in this setting, it's naturally that you may collect the data not sufficient to cover everything. What can we say beyond this data coverage assumption? Potential way to deal with such kind of stuff is we can explore some causal inference method, relies on your model, relies on your assumption. And I think this is, although it's not very satisfiable, but it's still reasonable. Why? Let's give a very, very hand-wavy argument. You know, human, and Newton is the top scientist among humans, and he discovered the Newton's dynamics only based on part of the observation, but it can generalize a lot of scenario which much beyond the observation he observed. The only reason is that the model is good. The model is perfect, almost perfect. I think same here. You cannot require too much beyond the say. You cannot require too much for the algorithm beyond the you don't have any assumption about the model, right? So I think potentially we still can incorporate some prior knowledge into this setting. Say even the data coverage not enough, but you still have a good model, you can still say something. That's, I think, something could be interesting, especially for the real world application people. To be honest, recently we are suffered from such kind of assumption. We don't in practice. Okay, I think roughly that's part 3. And before I go to part 4, any questions here?
So just to be sure I understood, in the algorithms you discussed, you use a min-max formulation, right? But in the empirical part, you always use neural networks as parametric approximator. And indeed, I mean, wouldn't that break, as you just said in the last open?
Yes.
Break the whole framework somehow. So it works good empirically, but is for now is a bit of a brute force from the theory side, right?
Yes.
Okay.
That's what I mean. It's still open.
Yeah.
To be honest here, you can definitely utilize the kernel and or linear model, and everything still, I'm not saying fully covered by theorem, but still covered a lot by theorem. I'm guaranteed a lot by theorem. And the feature, I mean, linear model, the feature part, actually you can extract, I mean, you can split this into 2 stages. One stage is you extract the feature, okay? And then you use this feature for parametrization. And so eventually in your model, in your optimization, in min-max formulation, it's still linear parameterized and convex and K. Everything's perfect and everyone is happy. That's one way to, that's a lazy way to avoid such kind of problem. Another one, as you mentioned, is definitely we really want to incorporate the neural network into the parametrization and learn it end to end. we not just train the final layer, but we still train the feature extractor simultaneously. This indeed is something very difficult. We only achieve empirical success by mimic again. We actually borrow a lot trick from how people train again.
But in the application that you saw, I was thinking about the one with the extraction of these words embedding these language models, right? There it seems that indeed these neural networks prove to achieve superior performance thanks to this, right? So having somehow to avoid that, probably we would need to pay a big price empirically, so to say, in terms of the performance, maybe.
Yes, actually, I skipped that part. If you go back to my slide there, it's like a combination of pre-train and end-to-end training. Actually, the language model is not just say you random initialize it and then plug it into the parametrization. It's done. It's not in that way. We to get a reasonable representation here, we first pre-train the language model on Wikipedia wiki. I don't remember the number. Wikipedia dataset. I think it's Wikipedia 18K to get a quite good initialization for feature representation. And then last layer is like a linear W transpose is phi as A.
Okay.
And then when I train it, I'm not just train the W here, as also train this representation. So it's like a hybrid. It's not to say I totally fix this part and the linear, or no, I use them randomly here. It's like I could have good initialization, which is pre-trained, and then end-to-end train both the final layer and this part.
So you use a sort of warm starting, but since you keep training the nonlinear component, you have a non-convex kind of element in your optimization, which makes it, which still brings us to the issue that you were discussing.
Exactly.
Okay.
That's exactly how I did it in the experiments. But I think you raise a perfect questions. This questions is, I don't think it's easy. I mean, when you introduce the neural network, what can I say about it? What can I say about optimization? Although I didn't mention anything here, but it's still open.
But from your plot, it seems that this, I mean, if one is able to use the proper theoretical tools and fix this kind of open question, then things seems to work nicely, actually, right?
Yeah. It's like empirical work, but theoretical we don't know.
Imitation learning. I mean, it's clear to me already by the cost function that you minimize, right? Since you take like the F divergence, right? You have this absolute continuity assumption. This immediately like gives rise to this data coverage issue. But so how about one would change this objective function to something that doesn't suffer from this absolute continuity thing, like a Wasserstein distance between, you know, like the behavioral kind of policy and the one that you optimize over? Could this be a way to kind of relax this data coverage assumption?
I don't think so. And I know your intuition, because the Versatile distance basically give you a transport between data to data, right? So your intuition like this will give the better way to avoid the ratio here. But I'm thinking that even that, I still think that we cannot say too much about beyond you don't have the data coverage. The reason is because eventually, we need the data to approximate the expectation in my constraint. So I don't know if it's totally beyond. I really don't know. See how this expectation. You mean? I mean, so as I mentioned, in important sampling, if your proposal is bad, so yeah.
Okay, so it's really kind of there must be some additional prior knowledge you can build in to say something beyond like the data points you covered.
Exactly, exactly.
And this is not so clear. What would that prior assumption look like or be?
Exactly, exactly. Recently, we really want to look into this data coverage in the aspect saying if we want to achieve such kind of, if we want to collect data to guarantee satisfy this kind of assumption, how many data we need. The result is quite interesting. I didn't cover here because we just submitted to NeurIPS, and it depends on how you sample. Let's say we distinguish sampling method into two different styles. One is say you can basically you have the generative model. You can do restart, which means you can sample from anywhere. You can acquire a sample from, say, I want to have sample SA, and what's next, so on and so forth. This is what we call it path independent, because it's just what I want it to do, right? In this setting, it's not that many. You just need a polynomial with respect to data and action pair. But if you use really execute a policy on particular MDP, and even the policy is universal. I mean, sorry, not universal, uniform for every action on every state. The number of samples is terrible. It's like exponential, exponential with respect to the horizon. It's straightforward because let's give a very concrete one. You have a chain, and each chain there is one separate state. So if you want to cover everything, definitely it's 2 to the h, right? So intuitively, that's the scenario. So what can we say? So that's why I'm thinking potentially one way to avoid such kind of assumption is we go to the representation part. That seems like lying in between of you require a particular accurate model and the data coverage. So you have a representation, and in the representation, everything is covered. You're fine. You don't in this setting, you don't need to worry about your model is accurate. No, it doesn't matter, right? You don't need to do that, but you still have a good representation. I think this might be a promising direction. And recently, my colleague actually tried this empirically. He didn't learn a model, just try to learn a feature. And in that setting, actually, eventually, the performance of the offline method is, even you use very naive one, say like the behavior cloning for imitation learning. We know theoretically it's debate, it's unbounded. I mean, the guarantee is, there's no guarantee for that. If in traditional setting, but even you use that with a good representation, you still have pretty superable performance empirically. So this makes me think that learning a good representation might be a good direction to avoid such kind of data coverage. This is what I'm thinking about this assumption. And it's echo what Mathilde mentioned. We can potentially separate this into two stages. And first, it's just seeking for the good representation. After that, linear model is enough.
Good. Yeah, thanks a lot. Thanks a lot for sharing.
Okay, we almost done with part 3, and I think we still have 1 hour and roughly 1 hour, 50 minutes and 10 more minutes here. I don't want to state the detail of part 4, but let's give a high level what I'm trying to explain in part 4. Part 4 actually is I will explain major component of part 4 is I will explain a recent result we obtained for global convergence of policy gradient. method with softmax representation of the policy, while with here's a little bit awkward with full gradient, with exactly gradient. So that's what I will cover mainly in part 4 about optimization based IL. And also I will cover a little bit about online exploration. That part is a little bit deviate from the major theme of my research, which is utilizing the optimization for reinforcement learning. But recently, after we want to extend this kind of policy gradient from full gradient, from full using exact gradient to stochastic gradient, we eventually it seems like it's not avoidable. And I think that's the two components I will introduce in part 4. Okay, let's start a little bit just to make sure we can finish on time. You're definitely also familiar with this slides. I copied from Niao's lecture. She gave a very good categorization of the policy gradient. So this is object function, and with different setting, either it's tabular MDP with non-parametric parametrization, or with function approximation for the policy. I would argue a little bit here. Actually, this is direct parametrization, but and also this is softmax parametrization. But I would say both of them are non-parametric. And this softmax parametrization is still unparametric because for every state action, you still need one parameter. The only thing it's eliminated from this parametrization is you don't need to restrict this parametrization to a simplex. Itself is a valid distribution. So in the following, we will think that we will introduce some recent advanced results for using policy gradient exactly policy gradient with softmax parametrization in tabular case. And here's something I want to emphasize. After we introduce this kind of softmax parametrization here, and back to this object function, I would say it is highly non-convex with respect to theta. It's not convex. So we cannot use the off-the-shelf results to achieve the global convergence. So that's something I want to emphasize at the beginning of this section 4. Okay, and actually this is proved formally in this paper. Okay, let's begin the journey. Before we start everything, let's first derive what is policy gradient. You definitely know this theorem. This is very classic theorem proved by Sutton in 2000. I think it's a NeurIPS paper. I will give a brief proof here, and hope we can go this quickly before this. We still have 10 minutes. I think we definitely can finish this part. Okay. First, let's ignore this proof, and believe me, this is the gradient, policy gradient with respect to theta. And then we can use the gradient to update the theta. So this is called policy gradient method. Basically, every time you calculate this component, this bigger component, this includes the expectation. And every time you use the step eta to update your current parameter and so on and so forth. This is what we call the policy gradient method. And in practice, we need to do some expectation estimation. So that's practical how, based on different way to estimate this expectation, that will generate a lot of different family of policy gradient variants, but we ignore that here at this moment. We just use this full expectation in this algorithm. Okay, so we are clear about the gradient, policy gradient, and the policy gradient ascent method. Now let's see how we prove this equation 8. Okay, from this first step, it's based on the definition of VPath. Okay, and then this is linear nebula gradient operator is linear, so we switch this expectation or summation with and this nebula, and this is by first part and gradient for first part and gradient for second part. So this part is easy. We don't need to change it. For the second part, we still, based on the definition of Q pi, we expand it here. And then use the linear property of gradient operator and make it inside. And R is independent, reward function is independent of the pi. So eventually we get to this quantity. And look, this is almost the same as this one. So recursion again. You see, in my slides, in the duration, there's the recursion is very important. We use that again and again. So I changed this part remember, I changed this part to 5. I don't want to write it. I'm a little bit. So for here, and for this part is like after step 1 from the distribution starting from state S to okay, this quantity is like for after step 1 and starting from S, the distribution of S prime. So that's basically this quantity. And this part we do expansion again. And similarly, this is rolling out again and again. Eventually, it looks like this term. And by the definition of this one, and also the definition of state and the definition of stationary state and action distribution, this quantity is eventually here. So we prove equation 8. It's not difficult, just tedious. It's not difficult, just tedious. Every time when you apply the basic calculus rule, remember, do the rolling out, and remember every definition of the quantity you will get there. Okay, after this slide, do we have any questions about policy gradient and the algorithm and also the derivation? Okay, so I think I will stop here, and let's start the final session 10 minutes later. And in the final session, I will discuss different variants of the policy gradient and also their global convergence and their rate. If time permit, I will talk a little bit about the exploration, because this is a reinforcement learning introduction course. I think we cannot avoid the major component in reinforcement, which is exploration versus exploitation. Okay. See you in minutes.
Yes, so we will reconvene at 5. Okay, but when you're ready, we are ready to restart.
Hi, hi everyone. Okay, let's finish the final session, and everyone will be released. Okay, now we finished the policy gradient and also the proof for how we calculate the policy gradient, and also we gave an illustration of how the policy gradient with full gradient executed in this algorithm box. And next we show some variants of the policy gradient. One of them is actually very famous. It's called natural policy gradient, which means after you calculate the policy gradient, instead of directly utilize that for updating your parameters, here's theta, you can use either the feature matrix to inverse of feature matrix to do a sort of preconditioning to update the policy, or equivalently, you can update the policy in this form directly to the theta. So although I read into the policy here, but equivalently, if we use the Softmax representation learning, Softmax parametrization, this here is theta SA. So it's equivalent to theta t plus 1 equals to theta t plus eta q SA. Okay, that's the this equivalent formulation for that. So this is nature policy gradient. And also we have another variant, which is called normalized policy gradient. Basically, instead of doing this, we do this. Simple. We don't use policy. We don't use the gradient directly. We use a normalized gradient. We call it normalized policy gradient. This algorithm actually is published in our recent work. Okay, here is some variants. Okay, I shouldn't address questions here. And also another big class of variants is like, instead of our ranged object function, you introduce the entropy regularizer into the object function, and then you can have entropy regularized policy gradient family. Okay, after you introduce that, actually the rest of the derivation is almost the same. Instead of you have actual component for the which is come from the regularizer. Okay, and then with this you can have the entropy regularized policy gradient, entropy regularized the nature policy gradient, and so on and so forth. Until now, I think I covered most of the representative algorithm in policy gradient. So you see this slide is familiar, but I separate this part into, we here give a very brief review of existing method, existing guarantee for what I introduced. Say like policy gradient with Softmax. Actually, nature policy gradient without entropy regularized is improved recently to exponential. But 1 over t rate is still unimprovable for Softmax parametrized policy gradient. And also, I think I made some mistake here. It's not 1 over t, it's exponential. It's linear rate for entropy regularized PG. I should correct this later. Sorry about that. And no matter whether with or without entropy regularizer for natural policy gradient, people prove that it's exponential, it's linear. And we also show that normalized policy gradient is also linear. The benefit of a normalized policy gradient is that in practice, you don't need to calculate the Fisher matrix anymore. Just do very naively do the normalization and use that to update your policy. That's good enough. Remember, this is saying softmax parametrization, but still non-parametric and exactly gradient. I think any part to extend beyond the non-parametric parametrization, say like introduce any function approximation and utilize stochastic gradient is not trivial. I would say there's some method trying to introduce stochastic gradient instead of exactly gradient, but they require very, very restrict assumption for the stochastic gradient estimator. And actually, we observed, and also people observed, which they have published paper saying this assumption normally is not satisfied in practice. But even that, sometimes your gradient, even that, sometimes your stochastic policy gradient still converge. And that's the paper published recently by Marlos and Nicholas from Google Brain, and it's published in SML this year. So that makes this things a little bit weird. It's not saying we can directly apply current result in stochastic gradient to stochastic policy gradient, because even the variance is unbounded is in stochastic policy gradient, sometimes still converge. Weird, right? But anyway, that's a little bit out of scope of this talk. Today I will just say recent progress in tabular case, softmax non-parametric, and exactly gradient. Remember, exactly gradient. Okay, so next I will give a very concrete example to show what's the major component to prove the global convergence. Actually, it's not difficult, but the proof actually is quite routine right now. But in this first paper, it's not that routine. But anyway, let's go back to the case study here. So it's softmax non-parametric plus vanilla policy gradient. Actually, this results V star minus VT is in red 1 over T. It's proved in May 2020 SML. The proof idea is utilize a smoothness assumption of this part and non-uniform lowest width condition with value suboptimality. So this will become routine. You will see how we can connect every component here to give this results. It becomes quite routine right now. So every different variance, just check this 3 conditions. You're good enough. You're fine. Okay, now let's first see the proof sketch. Particularly for this policy gradient, particular softmax non-parametric policy gradient, we can show that the value the policy value itself is smooth. I mean, Lyapunov smooth. And also this condition can be proved by checking the spectral normalization matrix of the gradient. As I mentioned, this is not difficult, it's just tedious. The next condition is very important, which is known as non-uniformly lowest width condition. The reason we call it non-uniform is because this is never a constant. Okay, this is never a constant. It's dependent on actually the theta. Okay, it depends on your current, the gradient of the current parametrization, current step parametrization. So this is also not difficult, chat. You just check the bound of the norm. And finally, it's also not difficult. Actually, we use many times. This is this condition actually can be obtained by expand the definition of this V function, and you do some and also some definition of the d pi and the q. You will get there. These are all quite straightforward. Now let's see how we can connect these 3 components into our results, into the finite convergence rate. Okay, step 1. We first switch from the station distribution to a uniform distribution value, policy value. So in this one, we know that expectation is with respect to the station distribution, but here we change that from station distribution to initial distribution. So you see there's some change, but you have some constant here, and we assume in our assumption this is not 0. This is not 0, which which you'll notice that this is also equivalent to in your initial distribution, your state and action pairs are visit everywhere. Okay, this is quite similar to the data coverage assumption. And then step 2, based on this one, we switch our object function from pi rho to pi mu, and then we can use the smoothness lemma to get this condition, which is saying the progress basically is upper bounded by this norm. Why is progress? Because you see, V star mu is never changed. So it's minus V star and minus V star, and it's canceled. So basically this is progress. And it's bounded by bounded by the gradient now. This is come from the smoothness lemma. And then we know there's NL inequality, or in another way, a non-uniform lower switch condition. So switch from here to here. Quite simple, huh? Now notice what's this? Basically, this is difference between the current solution to the optimal one. And it's also appear here. Remember, I just canceled the V star. Actually, this step is a little bit tricky. Let me tell you what it is. This, as I mentioned, this is non-uniform, which means it depends on current solution, right? So that I upper bound it with the smallest constant along your trajectory. So this is just because your condition is non-uniform. So you need to handle this non-uniformity by some constant instead of every step you have different constant. Now, actually, after obtain this one, first assume this is not zero. And after this one, actually, you already have the recursion to quantify the progress on each step. And basically from here, if you assume this one is not zero, you can already achieve this 1 over t with a lot of constant in front of it. But final step, you need to check this condition is indeed satisfied, which means this part is not zero. Again, this is still tedious. Let me tell the high-level idea. You need to utilize non-asymptotic analysis to show that this algorithm indeed converge everywhere in your simplex, except the boundary. Okay, except the boundary. That means as long as your starting point is not have zero probability for each arm, for each action, you're good enough to converge global optimal. Sorry, you're good enough to guarantee it never goes to zero during your optimization. And then because it's asymptotic, you can show that it never goes to zero. So this part is not zero. So combine this step 1, step 2, step 3, eventually you will have the conclusion. Okay, so come back to the high level idea. Three things. Actually, we use it in a different order. We first use this one to change the object function. And then we use the smoothness to let the progress is bounded by this quantity. And then use this one to map it back into the progress. Done. This is quite a standard recently. Become a routine algorithm already, a routine proof method already. So the only thing different is like with different algorithm, you will have different smoothness constant and smoothness condition and the different NL conditions. So it will form eventually different recursion that will give the different rate. I think this is why different algorithms behave differently. And difficult part, actually, I think the most special part is you need to check this part instead of have a constant bounded. You need to really check because you use the non-uniform Loyas width. You really need to check this constant is not zero. Otherwise, if this is zero, you can say nothing, right? So that means your progress is zero. So no, what can I say? Okay, this is basic. We use we gave a high-level proof scratch for Softmax with non-parametric parametrization for policy gradient. So we really do some empirical verification for our results. This is quite a simple MDP. It's only one state, and you have different, say like 20 actions. Roughly speaking, you can think of this as a bandit. And we just do policy gradient and we check the rate. So this is log t, and this is indeed the log t rate. You see, this is 1 over log t. We take, sorry, this is 1 over t and take log. This is curve, so match quite similar. And also we know the best one is 1, so it's indeed converge to 1. So basically we empirically verify our claim in a very simple case, which is manageable. Okay, so until now, I think I basically introduced the recent progress on global convergence of policy gradient family, and gave a case study of how we prove it in very basic algorithm. Any questions here? Okay, if we don't have questions, let's proceed. Okay, here's another case study, but I didn't complete the whole proof. I just show that even if you introduce entropy regularization, entropy itself is smooth, linear proof smooth with this constant. So plug this one with the original object function, it's still linear of ellipsis constant, ellipsis smooth, and then introduce entropy regularization will change the non-uniform lower Swiss condition. The basic thing here is it's no longer 1, it's 1 or 2. So that's why it will accelerate the convergence. And the rest of it is quite similar. Because this basically echoes what I'm saying. Now it's become the routine. Okay, so this is a summarization of not part 4, only a part of the part 4, which is the recent progress on if you use softmax non-parametric parametrization and exact gradient, how to prove these kind of results. Remember, smoothness condition, non-uniform layout of non-uniform lower Swiss condition, and value suboptimality lemma. 3 things. This is most important component to prove the results. There's some tedious thing, and it's tricky. It's just you need to check, because the non-uniformity, you need to check the constant is never 0. And combine everything together, we'll get the solution. I mean, get the conclusion. Okay, I think this is what I want to cover about the recent results. Okay, definitely have some open questions. As I mentioned, all these results are using exactly gradient. And I think there's one exception, which is came from recently particle mirror gradient from George Lang. But in his paper, actually, he have a quite strong assumption about the estimation of the gradient, which saying the estimation of the gradient is almost the same as exact gradient. So there's some noise, but no, it doesn't play too much effect. But as I mentioned, recently we noticed that this assumption is really rarely can be satisfied in practice. The variance can be unbounded. How we can, even the variance is unbounded, sometimes the algorithm is still converged, quite weird. How we can check, how we can provide some theoretical guarantee for that is still unclear to me. It's not answered yet. We have some initial thoughts, but we didn't finish the whole thing. We didn't close the problem yet. So this is one thing. And another one I think is quite interesting is if you introduce function approximation for the not Q, not in the way that, not in this way, not in, sorry, let's go to the first slide, not in this way. Not in this way. Not in, say, exponential phi transpose theta. This exponential family way, because sometimes your action will be continuous. So summation over the continuous space is sometimes intractable. What if I say just a Gaussian distribution for this action, a parametrization? That's actually another difficulty. I didn't see any results on that yet. But that one actually used a lot in practice. So I think there's still some gap between practice and theoretical results along this line. It's just the beginning. I would say, although the tabular case with exactly gradient and non-parametric parameterization almost finished, since many people came recently, but how to make it closer to practice setting is still don't know. Yeah, if anyone interesting, I think this is very good direction. Okay, so until now, I think I finished half of my section 4. And about the recent very hot topic about global convergence on using policy gradient for policy optimization. Any questions?
So you mentioned that when the gradient is not computed exactly, but rather we have an estimate of the gradient, so to say. So a stochastic gradient policy optimization, the variance could be unbounded, right? So there are some methods in the actor critic fashion that use, for instance, estimate of the Q function or value function to somehow try to bound the variance. Could you comment on that on the empirical? Yes.
Definitely. So
thanks.
That's still the case. It doesn't. It just pushes difficulty into policy evaluation, and that task is not completable in practice. The reason why is because, you see, let me give you a very intuitive or hand-wavy way to explain it. Even on policy setting, let's say the polytech, you need to make sure the QS is estimated very well, right? But in your current policy, maybe it's doesn't visit. It's not that flat. It's very sharp. Okay, so in that setting, you will only estimate some SA, not all of them. So that means your QSA for a different SNA, the variance will be huge. The difference of the variance will be huge. Some of them estimate very well, some of them are not. So in this case, it's really difficult to satisfy the assumption saying the Q function is estimated good, even you have on policy setting. So this is why I'm thinking that we should distinguish of the sampling policy and the optimal policy. The sampling policy should relatively, as we always observe here, have good coverage to make sure your estimator is good. But your control policy should be make it sharp, which means you need to go to the particular corner, which is best compared to other actions. So roughly speaking, this is already, you already see some shadows that there should be an exploration versus exploitation trade-off if you want to introduce the statistics, stochasticity in the estimation.
Yes.
This is my comment about this assumption about Q. It's not solving the problem. It just push some difficulty to assumption.
Mm-hmm. Thanks a lot. Thank you.
Yeah, if we don't have any questions along this part, I think I still have 20 minutes to give a brief introduction about exploitation and exploration. This is always a huge topic in reinforcement learning. I think I can make a claim that in Bandit, people understand this quite clear right now. But in MDP, it's still not sure. Still not sure. Oh, I shouldn't make such kind of claim because even in Bandit, if it's beyond the linear Bandit, I don't think any satisfiable result is satisfiable. So this is still a very active research area. Let's see, what is exploration versus exploitation? Actually, this is, as we discussed just it is induced by the stochastic nature because you never have the full information about everything. So you need to separate your effort, and part of them is trying to gather more information to know about your environment so that you have good estimation, better estimation. That's what we call exploration. But simultaneously, because you don't have, you want to still to achieve the best. You don't want to waste too much to estimate very well for some useless information. So that's what we call the exploitation. We want to make a better decision instead of estimate everything, right? So here I gave a quite a comic illustration. Say this robot want to pick a restaurant, and sometimes he goes to, as usual, he goes to this restaurant, but sometimes this new restaurant is opening. So if that's the case, whether he should go to there, and if he goes to there, that's called exploitation. That this robot use the chance to make a better estimation about the goodness of this restaurant. And if he goes to here, this is called exploitation because he already have very good estimation for the Euro place. And when we, in general, when we want to balance this trade-off between exploitation and the exploitation, the basic principle is be optimistic. Still, following this example, let me give an intuition why we want to be optimistic. If it's not optimistic, so every time it goes to the best based on current estimation, because this is never visited, so this is say like starting from 0, and this is positive, so he never have the chance to visit here. But if you use upper bound estimation, so because you never visit here, the variance of this could be very high and much larger than this one. So he will utilize some chance to visit here, and based on that visitation, he will shrink the covariance while eventually have a good estimation of the mean. So if this upper bound eventually is smaller than the Euro place, he will never go through here, which means he already located the best one. So you don't need to visit here anymore. So be optimistic means you need to give chance to other places. And vice versa, if that places is better than this one, you will never miss the chance. So that's the reason why we want to be optimistic, why we want to always curious about new chance, new challenge. I hope this gives the intuition why we need to be optimistic. Okay, mathematically, how that optimistic eventually initialized or eventually concretized into algorithm it's still like a multi-arm bandit, which is most simple MDP. Here you have two arms, and there's no state here. It's always say you play this arm, and you have a reward. There's no state change, so you always stay in that state. And the target of this multi-arm bandit is that eventually you pick the arm that's such that the reward is maximized. So in this cases, there's a famous algorithm called upper confidence bound algorithm, which is shorted as UCB. So the optimistic principle shows here is that every time you don't estimate the mean, but you estimate the upper bound. So which means instead of you just use the current empirical average to select, you also plus, which we call this bonus. And eventually this part gives you the optimistic part because here. So in this case, arm one is visit less. So shows in here is this part is small. So this bonus will be large. So he will visit this part. After visit that, he will have better estimation for the mean and also shrink the variance. And if the variance, if eventually the mean is smaller than this one, and also variance is shrink to slow below here, he will go to here. And this one will, this algorithm iteratively keep going and going. Eventually, we have guaranteed that this algorithm eventually will select the best one. And also, even better, we can control the regret, which means after you execute the optimum n step, the best thing compared to what you get, the best reward, the maximal reward, the oracle reward, compared to the algorithm, the reward achieved by this algorithm is upper bounded by square root of kn. And if you divide by n, which is average reward, it's, you see, square root of k over n, which means it's shrinking. Okay. So I will skip the proof here. But this one, okay, I will skip the proof here. It's a little bit tricky, but remember, this part is saying by optimistic, you estimate the upper bound so that you can bound the regret at every state. By current estimation minus true one plus bonus, and this part is controllable so that you eventually, when you accumulate this part, eventually your regret is in this rate. I hope this one gives you a rough understanding of what is UCB and what is implementation of the optimistic principle. Are we clear about this part? Great, great. If no questions, let's move to how this can inspire us about how we can move this kind of intuition to reinforcement learning. Okay, intuition. Remember what we did in UCB for Bandit. We used the collected data to estimate model plus some bonus. And this bonus just trying to make you be optimistic. And then you pick the best action from this optimistic model. That's what we do in UCB, in Bandit. Similar thing happens in MDP. You can use the data to estimate the model plus the bonus. Meanwhile, the only thing different here is that when you do the optimal action selection, it's not that easy to say max over all actions, max over all estimation plus bonus. It becomes a planning problem. So we use the value iteration to do that. And this gives you the algorithm called UCBVI, UCB value iteration. And I will give a algorithm box here. It's very simple. This part is counting. So it's tabular case. I will just focus on tabular case. This part is doing counting. And then the model can be estimated by this ratio from your empirical data. And the tricky part is here. It is giving you some bonus estimation. this part actually is doing the first component, which is doing the model estimation plus bonus estimation. And then, as I said, we can, because this is MDP, when you want to choose the optimal action from this optimistic model, it's not simple. So you need to do a policy evaluation. Sorry, not policy. You need to do a value iteration to select to do the planning and select the policy from it. Oops. And this one gives you the pi-t, and you execute the pi-t to collect data and do the iteration and so on and so forth. This is what we call it UCB-VI. And still, you can bound regret in a sublinear rate. And still, the key step is when you bound regret, you switch it to your upper bound, and this part is controllable. It's intuitively it is an extension of UCB, but because from banded to the MDP, it's a little bit tricky because you have so many recursions. So when the proof it shows that a lot of recursion you need to handle in bounding this term. I'm not going to detail, but remember this philosophy. And hope if you are interested, you can read the paper, and hope my explanation will give you a high-level idea of how they prove it. Okay, now I think I finished all the materials, and I think Niao covered a lot of other part. I only covered how we can use offline data, and also how we can use optimization to do with offline data to do the reinforcement learning. And here's my collaborator. And today I introduced a lot of work from a paper I co-authored with those guys. Dale from Google Brain, and Li Hong used to be in Google Brain, but now he moved to Amazon. And Jing Chen, Chaba, Wei Simon, Sherry, Ophir, definitely Niao, and Tor in Georgia Tech, and Inlam in Google. And thanks. And here's the reference I mentioned. I talked today. And thanks everyone. Listen to my 4 hours, such a long time mini course. I know it's not easy for everyone.
Many thanks to you.
Any questions? Any questions about either what I talked today, or we still have time, so we still have 10 minutes. So any questions about either what I talked today, or you can ask any questions about I didn't talk today.
I have some question, which, okay, is probably again vague, but since like this is a control kind of workshop, right? Maybe it's a valid question to be asked. So, so the methods that you presented, most of them like relied on a discrete action and state space. And so is there some hope of, let's say, some of the techniques presented or some of the tools to be lifted to give some answers to the problems where you have like, you know, like a continuous state and action space?
Definitely. I show it here just because it's simple and it's clean to give us intuition how we prove it. But actually, recently there's some effort to generate such kind of thing to continuous state and action model, which is called linear MDP, and linear mixture MDP. So although it's simple, but actually it's one good direction and to generalize what we did here to continuous state and action. Definitely, things beyond linear is completely messy. We don't know yet, but I think this some recently popular model to do some generalization.
I'm asking because, like, for example, you know, like you use, like in the first part of your talk, right? So you use like the LP structure of MDPs quite a lot. And there is some, you know, like early work of Benjamin Fenroy and and so on, where they have, you know, like LP structure for continuous space MDPs, and then they do constraint samplings, right? Because you still have like this for all state action pair constraint, which is infinitely many constraints. Yes. But you could think of then, you know, like applying approximation techniques there, such as, you know, like sampling, etc. So I'm wondering whether there's already like research activities on your offline MDP setting in this kind of general setup.
I would make some comment about the connection difference about this thing. A connection is definitely we both eventually make the infinite many thing to finite, and we use the stochastic sample to do the expectation, and they actually do a particular sample random projection. Actually, to be honest, these two are equivalent. But in my case, I make it into all policy setting and also make it behavior agnostic, which means I don't know who sample it. But in their case, I think they need to know the phi structure.
Mm-hmm.
So that's some connection and the difference. And what I want to say. Yeah, I think that's the connection and the difference. Both of us, we do some thing here, but still have some difference. Yeah.
Mm-hmm. Okay, cool. Thanks a lot for the great talk. Yeah.
Thank you.
Or lecture. Yeah.
Thank you for your questions. Yeah, it's actually just to pin the major drawback of this kind of method. But I don't know any other kind of method can go beyond this. It's still a very still quite open problem. Yeah.
No.
Are there any other questions from the audience?
Hi. Oh, sorry. Go ahead.
Okay. Thank you. I have a question that's a little bit related to what's the last question. What is your point of view? What is your opinion about model-based reinforcement learning method in the application of offline reinforcement learning task?
Okay, what kind of method? Based?
Model-based, like MOPO, model line plan.
Oh, model-based. Yeah, model-based.
Yeah, because I think they are more.
Yeah. I agree. I didn't mention this, but actually, if you look into offline setting, what I did is I do an empirical estimation first. You can always think I first do empirical estimation with data, and then what I'm doing there actually is doing planning with the empirical model. So that's why in my proof I said in the tabular case they are equivalent. Okay, and then come back to your questions whether which one I should use, either model-based or model-free. I think it depends. Some of the time, if you know everything about model, model-based, and that is not reinforced learning. That is called planning. So we should utilize model if we know it. But sometimes if we don't know it, I think we should avoid introduce any bias, which means model-based might be good in terms of approximation error. So I'm not saying which one is dominant the other one. I think it's case by case. Is this answer your questions?
Yeah, thank you.
Yeah, thanks also on my side for the course. And thanks for the effort of waking up so early in California. So my question was about the last part of the talk on the trade-off exploration exploitation, and particularly it seems to me that the UCB strategy works well asymptotically, and that's also what the regret analysis shows. But that also points out that in finite time you keep always accumulating regret because you need to then try all the possible upper bounds. So whenever you have uncertainty, you run the risk that you will go for something suboptimal. So
yes.
I was wondering if, in your opinion, it makes sense to formulate this trade-off more on a finite horizon problem where you have finite time and you have maybe some budget and you maybe accept some level of uncertainty to stay, let's say, with some level of uncertainty, but at some point you would like to stop being optimistic and just be greedy, because otherwise I mean, yeah, on one hand, I agree that you are solving the trade-off, but on the other hand, let's say you are doing it asymptotically. So it's kind of obvious that in the long run, you will visit everything. But I was wondering if it's possible to formulate strategies which are more finite time. And then you really have to play well, because
I understand your questions. I think we should divide this into two problems. First one is UCB in infinite many time and versus finite time. I think in Bandit, if I remember correctly, UCB already achieves lower bound, which means even in finite case, it's still the optimal. But when you say you want you don't want to observe everyone, you don't want to observe every arm. Let's go back to the data coverage setting. Let's go back to the data coverage setting. I think that's a good topic to work on. But we need to little bit cautious that the stochastic machine learning theory is not working for that regime. So you need to definitely trust your assumption. You definitely need to trust your model. So I was thinking that only your model is good enough, or your representation is good enough, such that you do that either relies on your model, relies on all your representation. You don't need to observe other things. Otherwise, it is require too much to enforce your need to achieve the optimal.
Yeah, so I guess that's a right way to maybe reformulate the problem. Is there a level of uncertainty in your system that you can tolerate? Hence, you can stop exploring as soon as you get there. And so you
Exactly.
Okay, I'm happy with that. Like going back to your analogy, I tried so many restaurants that no matter how good can be the end one that is opening tomorrow, I'm happy with what I already know, and I will go to the best one so far.
Exactly.
Because, yeah, I can be suboptimal, but yeah, I can tolerate that error, right?
Exactly. So it depends on your assumption, your model, problem model, and your eventually evaluation criteria, right? So definitely there's still many things to do. Yeah.
Yeah, thanks.
Any other question?
Any other questions? Yeah, I'm happy to answer them. Okay, seems like everyone is happy. So